you must be, you can recall in the last class we looked at the end we looked at gist of tropical climates, and what we said was generally the tropical climates we classify them, main classification is hot, dry, warm and humid, and composite monsoon. And Indian standard, of course, energy code, ECBC, energy code, energy conservation building code or national building code, they classify it into now 5 zones. Earlier it was 6, now they have made into 5. So hot and hot, they call it hot and dry, and then warm and humid, and temperate, cold and composite. Now this is, of course, this is typical of Indian scenario, because in the tropical climate we have altitudes, Himalayan areas, and even the Deccan Plateau, Nilgiris and all those, Aravalli, Mount Abu for example, it's not, although it is in desert, but its temperature is much lower. It will possibly fall somewhere maybe in the temperate climate or whatever it is. So that's how it is. So these are the classifications we saw. Now having looked into those classifications and their characteristics which you have seen earlier, I said that this is mostly useful when you are doing a kind of a thumb rule based design. But you get some rough idea. Okay, composite monsoon climate, you have both heating and cooling, those are the issues. From thermal aspect, heating and cooling, those are the issues, right? Daylight, of course, you would like to get everywhere. Other thing, that noise is man made, so therefore there is not much to do at the moment with the climate. If you look at it hot and dry, then humidity is low. So it's obviously cooling is a requirement, but at the same time humidifying is also a requirement. You would not like to make it, it's dry. And warm and humid, again cooling is a requirement, but dehumidification may be a requirement if it is an air conditioning system. But if it is natural, then natural ventilation can remove the moisture from the body, So that's the basically a kind of thumb rule you can understand. Now we can follow the next part, that is you can look into what you call thermal comfort, and that would give you an idea why you are saying cooling or dehumidifying etc. is required, and we will look into thermal comfort now. So in general, if I look at thermal comfort, deep body temperature is 37.4 degrees centigrade. That's that's supposed to be the understanding. In fact, body will have its heat transfer. This is the human body. Let's say the sun is there, the cloud is there, or wherever you are. So you receive heat from outside, from the surrounding. Even within a room, you might receive heat because the walls are warm, right? Walls are warm and it is transmitting heat. So there will be heat you would be receiving by radiation. If you are touching with something, then there can be conduction, gain of heat also. And if there is air around, surrounding air is there, then there may be, and it is hot, there may be some heat transfer because of hot air coming in contact with your body, right, and heating it up, and the circulation pattern might be there. So if there is fluid around the body, because there is a fluid around the body, the air, there will be convective heat transfer from that fluid to your body also, as you shall see the basic modes of heat transfer. So heat gain can take place by conduction, by radiation, and also by convection, and there can be heat gain from the body, because whenever we are, you see, some parts of the body never stops working. For example, heart. So it's pumping blood all the time. Now if it is pumping blood all the time, that means certain work is being done, and in that process everything, all the energy, some energy would be dissipated as heat, because there will be losses at the artery boundary or veins boundary or whatever it is. So the body generates heat all the time. That's called metabolic heat generation. So body generates heat all the time, and it depends upon the activity that you are doing. For example, when you are doing something like lifting, it generates more heat. If you are doing sedentary work, it will be somewhat less. Sleeping, it will be least, because many of only certain parts of the body is active, others are not. So another mode of heat generation is the internal heat generation of the body. Internal heat generation of the body. So this is how body generates heat and receives heat. Now how does it dissipate? Because it has to maintain that constant deep body temperature, otherwise you will start feeling a kind of a discomfort, so you will feel warm, and if it goes below, then also you feel cool. So dissipation is loss of heat is again by conduction. There can be loss of heat by conduction, heat loss can be there. Radiation heat loss can be there if the air or the surfaces surrounding is at lower temperature. Then there can be conduction loss, convection loss as well, if the surrounding air is cool. So cool air comes in contact with the body, gets heated up, will move upward, so there could be local circulation and things like that. Together with that, body can actually lose some heat by evaporation from the skin. Evaporation from the skin. And this evaporation can occur if the moisture is present. And if the surrounding air has a capacity to absorb that moisture, then it can lose heat, right, evaporation. So that is latent heat can be lost. So you can see that loss by sweat mechanism. Sweat mechanism. What happens when when you are, let's say you are jogging or something, surrounding temperature is also quite high and you are generating metabolic heat at a very high rate. In such situation, what will happen? Body cannot lose heat, because body may not be able to lose heat because the outside air is warm. It is not able to, in a closed room, let us say you are doing, and the surfaces are also quite hot. So radiation heat transfer is not possible, or is less, and because surface is at higher temperature, your body temperature and surface temperature difference may not be too large, air temperature and your body temperature difference may not be too large. So what happens is, under such circumstances, or if the body wants to dissipate heat at a faster rate than otherwise naturally occurring, what it does, it first increases the blood circulation of the skin. So skin temperature increases, such that now skin temperature is higher than the surrounding, heat losses can occur, because heat flows from higher temperature to lower temperature, sensible heat. If that is one mechanism. Second mechanism, it starts generating moisture at your surface. The tissues, the skin tissues would start actually generating moisture. It is a body moisture. So you can have dehydration. If it is too bad a situation, a lot of moisture loss from the body would be there. So what it would do? It would then, if the surrounding air is dry, evaporation loss would occur, and it will take the latent heat of evaporation from the skin itself, and thereby body temperature will come down. So you see sweat mechanism. Besides that, our breathing, exhalation, we lose some heat through that as well. So you can see this is exhalation, and then sensible heats actually, various kind of this can, many of these, even this exhalation also we lose some moisture. So all this causes some sort of evaporation loss from the body. Now just in cold situation, what happens is, loss of heat from the body is too much from the skin, outside is quite too cold. So your deep body temperature tends to go down, right? Body should be generating more heat then. So shivering mechanism allows additional heat to be generated in winter, and in summer sweating mechanism causes. So that's how, and doing all this, body tries to maintain, of course, deep body temperature to the required level, that is 37.4. So the losses, as you can see, losses are by evaporation, radiation, convection and conduction. Gain is by convection, conduction, radiation, shivering and metabolic activity, vessels metabolic activity. By that the gain takes place, right. Everything do not go on simultaneously, because shivering and sweating will not occur together. So that is how it is, right. So that's thermal comfort. Okay. We will come back to this sometime later on again. We will come back to this sometime later on again, when we are we have looked into basic mechanism of heat transfer, right. So, I thought I will give an introduction. So, now you can look at, because supposing I want to find out the heat transfer from the body, put it in generalized equation form, because that is how we generalize, right. The algebra or mathematics can generalize the whole thing. So, this physical thing. So, when we want to do that, then what we will do is we will actually before that we got to know the basic mechanisms of heat transfer. Now, since your background, in civil engineering or architecture, you may not have done much of a heat transfer. I would like to talk about some of the basics of heat transfer as well. So, that is what we will do. Okay. So, first we will look into that, and then heat flow, basically heat flow we will look into, but heat flow in building will come later on, but basically first I will see, we will look into heat flow itself. So, that is what it is. Initially we will start with heat transfer concepts. Now, you see heat flows from sensible heat, as I am saying. There are two mechanisms. One is the sensible heat, and measure of the heat content of a body is the temperature. Temperature is an indicator of how much is the heat content of the body, right. And heat flows from, or for that matter any flow takes place from higher potential to lower potential. Now, in case of heat flow, the potential is the temperature, because it is basically, if you look at the heat content, basic equation you would be remembering. Specific heat, for example, how is specific heat is defined? It is the amount of heat required to change the or increase the temperature of the body to 1 degree centigrade. Of course, is compared to specific heat of water, that is from 14.5 to 15.5 and etc. So, unit mass of the body, if you want to raise through the temperature, right. So, you see all potentials, if you look at it, potentials are defined in terms of for example, gravitational potential would be h, height, mgh is the potential energy per unit mass, if you take, or electrical potential per unit charge, etc., etc. All you take in terms of per unit value. So, here mass for the temperature is nothing but is the temperature is the amount of, specific heat is defined as the energy required to raise the temperature through unit mass. So, yeah, for 1 degree centigrade, specific heat is defined that. So, specific heat, so therefore, mass into specific heat C, we will be denoting it by C. Delta T is actually energy, let me write it right now, not formally. So, energy per unit thermal mass, that is basically your potential. Any potential we define in that manner. So, temperature is nothing but kind of a potential. So, if there is a temperature difference, heat will flow from higher temperature to lower temperature. It is analogic to electric potential, right, which is the work required to move a unit charge, and if you look at potential in case of gravity, then it will be work required to raise the body through unit height, something like that, So, something of this kind, some analogy I am trying to draw. So, temperature difference causes heat flow. So, conduction, 3 modes of heat transfer are there, as you would be remembering. Conduction is one of them. When heat transfer occurs to solid body because of temperature difference, that is what is that mechanism, we call it conduction. So, let me consider a dx element, and let us say other dimensions are dy and dz, and I have some heat flowing from one side and the other side q plus dq, the other side the heat flow. Now, this is heat flux, which will be written in terms of amount of energy joules per meter square per second, rate of heat flow, heat flux per unit area per unit time. So, this is nothing, what is the unit? Watt per meter square. So, heat flux is watt per rate of heat flow per unit area, and let us say heat passing through, this is this could be plus or minus q minus dq or whatever it is. So, that is what it is, right. Now, Fourier's law, it says that q is proportional to temperature differential for example, if I have temperature dT existing between these two, temperature difference existing between these two, say over this distance dx, other side they are all insulated, no heat flow is occurring, then conduction heat transfer, this Fourier's law, the amount of heat transfer or heat flux is proportional to temperature gradient, and you would have seen similar equation, Darcy's law. In soil mechanics you would have come across Darcy's flow through porous media or soil, where the flow is proportional to hydraulic head gradient, head gradient that is what you say, and many places you will see that it's related to that. So, this Fourier's law, if one goes to the very fine level of conduction, that is actually vibration, crystal vibration and all that, we are not interested, we are looking at the macro level. So, for constant T with time, there can be two situations when T here and T here is constant. I am saying no heat flow there is no heat flow in this direction, or this direction or this direction, only one dimensional heat transfer is occurring. And if I maintain constant temperature here, constant temperature at these two places, that would be, if the temperature is remaining constant, still heat flow will occur, because dT might still exist, and that we call steady flow. Steady or static, where it is time invariant, it is not varying with time, and as opposed to that, for T varying with time, that is non-steady state flow, right. So, in such a situation, non-steady state flow means there would be, when there is non-steady state, that means temperature is changing with time, right. So, under such situation, actually there must be some heat stored in the element, because heat coming in minus heat going out, and if my temperature is constant, whatever is coming in must be going out, otherwise temperature would have changed, So, in a steady situation, heat coming in must be equals to heat going out. Now, if it is not so, which is in case of unsteady state, that means some heat must be stored in the element. So, therefore, heat stored in the element per unit time is the difference in incoming minus outgoing flow, when Q is a function of time and space, which is here, and then it can be function of time and space. So, therefore, one can write dq, one can write like this, partial derivative, because now it is time and space. So, that is why I am writing in terms of partial derivative. Q is a function of time as well as space, because it is unsteady state. So, it is changing with time as well, and it will vary, it might vary with the space also. So, therefore, that is what I write, and Q minus dq plus Q dq, because whatever is coming in is this, whatever is going out is this, right, whatever is, because that is what I have written in that previous diagram, if you have seen, into dy dz, that is the area, because this is flow coming in per unit area. So, this is the flow per unit time, this is the flow per unit time, this is the flow per unit time, that can be written as minus dq dy dz, am I right, minus dq dy dz, right. Go back to this previous diagram that I had, what I am saying is coming here is q, here q plus dq. So, q minus whatever, this must be this. So, this must be stored in the system, because whatever is coming in minus whatever is going out, that is what must be stored, and if it was steady, then no storage would be there, whatever is coming in must be going out, that is why temperature is remaining constant, but still there will be flow. So, T is a function of time and space, and therefore, dq will be written like this. Now, we said that Q, we just, if you recollect, dq, so Q was k dt dx, right. So, dq can be written as del of this one. So, that is what I am doing, del x of with space, if I am doing, I can write it like this, k dt dx, because this is the flux q. So, dq can be written like this. So, dq dy dz can be written in this manner, dq is written from here like this, right, and dx dy dz, that is the volume of the element, right. So, how much is stored in that element during that period of time, this per unit time, and supposing this occurs in dt time, small dt time, this is the amount of heat transfer that is occurring over small dt time. So, this is the amount of heat stored in the dx, dy, dz volume in dt time, small del t time. No? So, this is this is what I have done. What I have said is whatever is coming in minus whatever is going out is this. Q can be written in this manner, right. So, in partial derivative form I can write it in this form, partial derivative form, and dx, dy, dz is the volume of the element, volume of the element. So, this must be equals to stored heat stored in the element per unit time is the mass into specific heat into rate of temperature rise, right. So, therefore, I can write it like this: mass is nothing but rho into volume, that is m is equals to rho density into volume dx dy z. C is the specific heat, that is how we defined a little bit earlier, and rate of temperature rise is del T dt, because per unit time how much is the temperature rise, that must be. So, that is what I said, the heat flow per unit time was dq, right. I did it for unit time, the flux was watt per meter square per second. So, rate of change of temperature, temperature rise is given by this. In other words, I can equate it like this, and this gives me the basic one dimensional heat transfer equation. If I remove this 2, this will give you the basic heat transfer, one dimensional heat transfer equation, and that is what it is, right, k del T square, right. This well known equation, macro level engineering, heat transfer equation basically at that level, for large bodies like wall and roof and things like that, we can apply this equation straight away. So, that is the basic equation of heat transfer, right, the conduction equation, and we have taken it one dimensional. If it was 3 dimensional homogeneous isotropic material, K will be same, K is the thermal conductivity, rho C will be same in all direction and for all, it will be same throughout for a homogeneous isotropic material. Homogeneous material means it is same, isotropic means on all direction it is same. So, this property and this you can combine and we call it thermal diffusivity. K divided by rho C, we call it thermal diffusivity. We will come to this sometime later on, we call it thermal diffusivity. Again we will use this sometime later on. So, this is basically conduction phenomena and conduction heat transfer. Let us look at convection. So, convection, Newton's law of cooling. Now, solid bodies, they are not isolated, they are always in some surrounded by fluid. If it is my human body, I am looking at thermal comfort or the wall, there will be fluid around. Therefore, heat transfer takes from the solid to the surrounding fluid, right. So, Newton's law of cooling is, temperature versus time. If you plot, this is time of a body and this is temperature, then you find it is something like this. In fact, one can show that convection heat transfer, it is proportional to hot body minus temperature difference between hot body and cold body, and this is called coefficient of convective heat transfer, convective heat transfer coefficient. I had something similar I talked about earlier when I was talking of relative humidity. So, H is the convective heat transfer coefficient, right, convective heat transfer coefficient. So, this is the one dimensional again convective heat transfer. So, H is convective heat transfer coefficient, right. We used it sometime earlier, and what will be its unit? This is watt per meter square, this would be degree centigrade or Kelvin, whatever you call it. So, watt meter square, that is what H unit of this will be something of this kind. What was the unit of thermal conductivity? What is the unit of thermal conductivity? Unit of thermal conductivity will be, because we said Q is equals to K dt dx, right. So, this is watt per meter square and this is degree centigrade meter. So, it will be actually watt meter degree centigrade. Unit of K will be watt meter degree centigrade, right, watt meter degree centigrade, okay. And unit of convective heat transfer is watt per meter square degree centigrade. Let us look at radiation now. Okay, convection there are two parts. Of course, what I said was it is a part of the temperature difference only, but supposing I have a wall, right, from the wall to the surrounding, from the wall to the surrounding, this is the wall part of it, let us say this is my wall surrounding, heat transfer will actually occur not by convection alone, but also by some radiation also, because there is a temperature difference existing. We will define the radiation part later on. So, some radiation component I can equivalent H when I write, or surface coefficient of heat transfer at the surface of a wall or a ceiling or something of that kind, or outside roof. So, I will have two component Hc and Hsat. This is the related to convection, some portion will be related to radiation, and we approximate them linear, take them as linear and sum it up, we can sum it up. But this one will have again two components. What are those two components? We wrote that it was T h minus T c, Q was equals to T h minus T c. Now, supposing this, if I have a air stream moving at the surface, temperature difference will cause, actually convection is what? It is movement of the molecule. Conduction is essentially solid crystal to crystal. So, you have one molecule to another molecule, they are in contact, or one grain and another grain they are in contact, and heat transfer occur through contact in case of solid. That is what is conduction. Is conduction. Like the school days, they used to give us a good analogy that supposing I have a huge quantity of pieces of brick kept on one door, and we want to transfer it to another corner, or some 10 of us or 20 of us stand up in line, take one heat, pass to the next person, and pass to the next person, and pass to the next person. That is kind of conduction. The molecules are not moving, but if you take the same number of molecules, take one brick, run to the corner, drop it and come back and take it, that is convection. So, actually in convection molecules move. For example, you have a beaker, you are heating the water molecule will, what will happen? Their density reduces, there is a buoyancy effect, because once you heat it up, their mobility increases, all theories, kinetic theories and all. So, their mobility will increase, the molecule Brownian motion will increase, and their density reduces. So, higher density one tends to go down, lower density ones. So, hot ones will go up, cold ones will come down. So, there is a circulation. So, in case of a wall, similar thing would happen. Hot, if the air here is hot, there here it is cool. Let us say air here it is cool. Let us say cool air here, cool, hot here. It's hot actually. It's hot. So, this is hot here, cool here. Now, what will happen? Hot air will have a tendency to go up, and cool air from this side will go and fill it in. In other words, there will be a circulation pattern. So, that is convection, right. Now, supposing I have a air motion here on the horizontal, there is a air velocity, air is moving, velocity is there, wind or air movement is there, air flow is there. What will happen? The rate of movement of the molecule will increase, so it will actually carry the heat more. So, that is called forced convection. For example, you have a fan causes more cooling, so that is forced convection. So, there is one component related to the velocity, forced component, and there is the other is a free component. So, one is free is because of the temperature difference, forced is because of the air movement, air velocity present. So, you can actually divide it into two parts, and Hc is some constant into V velocity. This one is a function of Hcv, actually is some k dash into V, function of velocity, but we do not look into that details, we are just trying to understand them, that is all. So, this is related to velocity, this is related to temperature difference, this is related to temperature difference. There is a radiation component also. So, Hc is equals to Hf plus Hb, one can write. So, Hn are free and forced convection heat transfer coefficient, and we sum them all up together and we call it surface conductance. Sum them up all together and call it surface conductance for wall, right, or coefficient, surface coefficient, heat transfer coefficient for wall, as well as ceiling, roof or anything solid surface in contact with the fluid, right. Now, then we can look into radiation heat transfer, Now, radiation heat transfer, the same analogy, if all of us stand there and that corner we have to transfer the break, what do? You throw it. No movement of the molecule, no contact of the molecule, you do not require even, I mean even a medium in electromagnetic radiation, you do not need a medium, while of course mechanical waves there will be a particle to particle transfer, local vibration of particle about the mean position of equilibrium, but heat transfer can occur. For example, sun's radiation comes from that far, right, and it does not require, it is not necessarily there is a medium there. So, the equation is given by, radiation heat flux is given by this equation, Th to the power 4 minus Tc to the power 4, Th hot, hot temperature, hot surface temperature to the power 4 to the cold body temperature, which is Tc to the power 4, multiplied by Stefan Boltzmann constant. Stefan Boltzmann constant, this is called a factor, viewing factor, we will have configuration factor, and these are equivalent emissivity. Now, let us define each one of them. Epsilon is equivalent emissivity, sigma is Stefan's Boltzmann constant 5.7 into 10 to the power minus 8, F is called configuration factor. What is F? For example, if two bodies are facing each other, then they are seeing the complete thing, right, is 1, but it is something like this, then projection of this one over, there is a common projection, that is what would be seen. So, the amount of radiation heat exchange between this condition and this condition will be different, this will be lower. So, there is a factor geometry related to the geometry of those two spaces, that F is a factor related to that. For example, I have a surface dA 2 and dA 1, these are the angles theta 1 and theta 2, normal to them, direction of their direction, that joining their center points are something like this, normal to this surface is this, normal to this surface is this angle is theta 1, this angle is theta 2, then the F would depend upon this F would. Supposing this was theta 1 and theta 2, they are both 0, that will have been maximum. So, this is related to those. We will not look into that details actually, but this is a radiation heat transfer. What is equivalent emissivity? It is a combination of emissivity of the hot surface and cold surface. Now, what is emissivity? A perfect black body absorbs all radiation, right, it absorbs all radiation, and at the same wavelength it will emit that radiation also, because it will get heated up. So, it will, if it absorbs all radiation, it will get heated up, and it will become too hot, then it will give away those radiations also. So, emissivity of a body is defined with respect to a perfect black body. It is a relative, in a given wavelength, relative fraction of energy it will emit compared to that of a black body, that is how it is defined. Emissivity of a surface involved radiation heat exchange. So, the two surfaces will have different emissivities, and the equivalent emissivity epsilon AB is given by this formula -1. So, epsilon A and epsilon B are emissivity of surfaces involved in radiation heat exchange. Again, we do not have to really get into that, calculate those ones, because epsilon, we will simplify this for our purpose, we will actually simplify most of them, but this is a principle, all right. So, FAB, so radiation heat exchange between two bodies will be given by FAB. FAB is configuration factor, epsilon AB. AB is the area, AB is the area, AB is the area of one of the bodies, sigma Stefan Boltzmann constant Ta minus Tb to the power 4, right, Ta minus Tb to the power 4. So, that is what it is. Now, which means that radiation heat transfer is non-linear, it is T to the power 4, right. But if temperature difference is small, Ta minus Tb is not very large, then we can approximate it in linear manner. Let us see how we do it. Over small range of temperature, radiation heat flux expressed as a linear function of temperature differential. because instead of writing T to the power 4, I can write QR is equals to some those constants dt to the power 4. T to the power 4 T1 minus TH minus TC to the power 4. This is nothing but I can write it as dt to the power 4. Temperature, difference in T to the power 4, right? Small difference in T to the power 4. If this temperature differences are not too large, which can be written as 4 T cube dt. So, when this TH minus TC, TH is not too different from TC, you can approximate it as 4 K T to T cube dt. In other words, you have actually converted into a function of difference in temperature rather than temperature to the power 4. So, for our condition of building heat transfer in normal condition of from environment to inside, we do not consider it to be T to the power 4 nonlinear manner. But if you are dealing with fire, where temperature can go up to 1000 or 1200 degrees centigrade, you cannot take it in this linear manner. So, here it would be 50 degree, 25 degree, order difference of difference is not very large, we take it as simply something of this kind. So, you linearize it. So, our HR, that is why we could write that HR, if you remember, we talked of HR, we did talk of HR. So, HR which we said was H is equals to HC plus HR, and these are two component. This HR is now some constant into temperature difference, because this we are saying the heat transfer will be proportional to H, let us say wall minus the T air. So, this wall to the air, the temperature difference is not very large. So, we combine and write in a linear manner, and approximate values are available with us, and that is how we handle. So, that is the basic equations of heat transfer, We can little bit look into heat flow path in building. Yeah, we can little bit look into heat flow path in the building, but maybe just after a small break we will do that.